So my name is Riley Beddoe. I'm an associate professor at the Royal Military College of Canada, which is in Kingston. And it really is an honor to be here to talk about some of the research that I've been doing over, I guess, my academic career so far. And it has already been said, but I would just like to repeat it. I really wouldn't be here without the financial support from the CFG and the CGS. And so together they're able to put some money and allow me to actually travel. So I've been out east and I've been now out west. And my hope is this fall I'll be able to actually go north and visit Whitehorse and Yellowknife as well. And so a huge thank you to the CFG and to the CGS. And I will say, Jack, when you did the financials, I was like, wow, what are you spending $80,000 on? But to actually do that and put it back to the CFG, that's a really commendable thing to do. So that's awesome. Okay, so why am I here? I'm here to talk a little bit about permafrost. And so this is a schematic that I like to put up that talks a little bit about permafrost and its distribution across Canada. It is done with, pencil crayons. It's not my work, but I love this map because what I don't want to do is to get into the nitty-gritties of where there's permafrost, where there's ground ice, and where there's not. There's really good and important people who love that kind of thing and spend a lot of time talking about it. That's not going to be me. And I think this map does a sufficient job for what I will say. But maybe worth it to say, how many of you feel that you would say, yeah, I know something about permafrost. I feel like I could talk about permafrost. I know there's some of you in this room. Yeah. Sam, Jim, your hand, come on. Okay, awesome. So I will say that I'm an academic, sort of, not at the very start of my career, but sort of getting into my career. And so there are experts in this room that know much more than I do. And so if you have questions at the end of tonight, I'm going to point you in their direction because they're the experts. How many of you perhaps don't think much about permafrost or really are like, I don't know? Then you guys missed out on Jocelyn's talk and shame on you. No, that's fair. So there's some of you who don't do a lot about permafrost. And so my hope is that I'll be able to speak throughout this presentation to everybody in the room. But if I'm talking about something that I haven't maybe started explaining well, please raise your hand, ask me a question, because otherwise I'll lose you. And it's more fun to sort of stay understanding what I'm trying to say. Okay, so permafrost in Canada, this is a bit of a map, and we have dark blue on top and light blue sort of as we move further south. And that's representing what we call continuous permafrost, where you imagine there'd be permafrost sort of, not everywhere, but most areas. And then as you move further south, we have sort of discontinuous to isolated patches. So you can imagine a north-facing slope might still have permafrost, whereas a south-facing slope wouldn't anymore because it's been exposed to that solar exposure. What's really important to think about is that we have all of this permafrost that's happening, but everywhere where there's no permafrost, we're still in Canada. And so we also have a lot of frozen ground, right? Down here in Calgary, I have it in Kingston, albeit not that much in Kingston. But we have frozen ground. So while I'm talking about permafrost, it's sort of, we can all think about it that it applies to all of us in some way, shape, or form in the work that we do. But we can imagine also and understand that it's going to be impacted by our warming climate. And so what I love about this figure is it really visualizes the increasing air temperatures and the amplification of that temperature rise that's going to happen in the Arctic. And so I love this sort of graph because it really shows that the mid-century isn't looking good for the Arctic. And we can really see how much warmer the Arctic is going to be compared to other parts around the globe. And so when we couple the warming air temperatures and permafrost, we can imagine there's going to be some challenges. And so what we're trying to do is understand how this changing climate will drive permafrost change and what these changes will look like. And so sometimes these changes are large, right? And they're very large, they're landscape scales. And we might see things like the coast of the Northwest Territories, where we can see that we have large portions of the coastline eroding and failing and sinking into the sea. We might have large thermokarst events like this retrogressive thaw slump, which is massive on scale. And imagine that it's happening near the Dempster Highway. And so you can have these large interactions and large processes that are going to impact linear infrastructure that we use. Sometimes, though, these changes are actually quite small, and they happen much smaller infrastructure and much more site-specific. So here's an example of a corrugated steel culvert that has experienced ice jacking, right? And so with this water, as we have freezing temperatures, we have ice that's going to grow, and we're actually jacking this culvert out. We can imagine that this culvert is no longer performing the way it was designed to perform. And then we have simple things like embankment failures that can happen. So we can have warming that's occurring on these embankments. Often that's sort of correlated with snow, perhaps, but these embankments which are then going to impact this highway. And so it's not a large failure by any means, but when this is the one and only highway, it has a huge impact on goods, commodities, communities, etc. And so what we're trying to do is understand how this changing climate will drive permafrost change and what will be required for cold regions geotechnical engineering. And so that's kind of some of the big picture thinking that me, my students, my colleagues all think about when we're sort of approaching some of our research questions. So today, rather than diving into one area specifically, I'm going to jump around a little bit and talk about sort of some of my students' work and what they've done to sort of help us understand how we have environments and infrastructure that's going to change and how we're going to sort of shift and support consulting engineers and those who are designing and constructing it in those endeavors. Okay, we're going to see this map a whole bunch of times. And we talked about permafrost. And permafrost is ground that is frozen for 2 or more years. And so when I say frozen, that has something to do with temperature, right? And so you can think about the fact that when we're talking about permafrost, there's a huge importance to temperature. And so we can imagine that the temperature in the ground is going to be an important thing to know. And so the first thing I'm going to think about and talk about is permafrost temperatures. So the condition of permafrost, we might then correlate to what those temperatures are. And so we can understand that knowing the ground temperatures are extremely beneficial. But that being said, the Arctic and permafrost zones across Canada are very large and vast, and there's limited thermal databases. So limited areas where thermistors have been put into the ground are recording temperatures and then are available for use by researchers, public, etc. There's a number of thermistors that aren't on a map like this that have been installed from consulting or site-specific, and trying to put those together is a challenge. So one of the things that the Northwest Territories Geological Survey is doing is they're actually trying to put together all of that into a permafrost database, and I think there's hope that this will transcend elsewhere, okay? So one of the things that we can notice, though, is that there's very specific locations where there are lots of thermistors recording ground temperatures, right? So Mackenzie Valley Pipeline, that now Mackenzie Valley Highway area, sort of some in the east, in and around Hudson's Bay, but there's a large area of Canada that there's not a great record for permafrost temperatures available. So with my RMC hat on, I'm actually able to work with the Department of National Defense. And so in that work, we've actually had the opportunity to look at a data set and use a data set of thermal temperatures. And that map of locations looks like this. So anyone want to know what these locations are that I've identified? Yeah, the dew line. So this is the dew line sites. And for those who don't know, the dew line was built by the US and Canadian military sort of back in the late 1950s. And it was an early warning detection system for incoming air raids. And so it basically spans the 70th parallel. It goes from the United States, Canada, Greenland, and Iceland. So it started in 1955, and by 1994, with improvements to technology, they were decommissioning these sites and putting in a new north warning system. So part of that decommissioning of the site was building engineered landfills, where some waste was going to stay on these sites. They removed much waste as well and contaminated soils, but lots of was left and built in engineered landfills. And part of those designs were to try and keep the waste frozen, right? And so if the waste remained frozen, then the idea is that it will stay nicely input and it's not going to contaminate or migrate, and you're going to have a frozen landfill that's performing as designed. You put a cover on it, we're good to go. In order to say that, yes, the design is working, they installed thermistor cables to monitor the temperatures in those landfills. And that's where we come in. So we've been able to look at this data that's being collected across the 70th parallel of Canada to sort of look at what those permafrost temperatures are. And so what does it look like? Well, if we jump to Cam, Maine, this isn't like there's one thermistor. Here we've got 3 landfills, and in each landfill, there's a different number. So there's 4, 3, and 2 thermistors that are installed. And so this gives us a really interesting opportunity if we wanted to look from one specific site, what different thermistors are doing in different landfills, et cetera. So what does one of those thermistors look like in terms of the data? Well, here we've got what's called a trumpet curve. On our y-axis, we're plotting the depth into the ground. So 0 is going to be at the ground surface. On the x-axis, we've got temperature. And that 0 degree, right, which is going to, and obviously this is not pure 0 degrees, but anything to the left, we've got frozen, and anything on the right of 0 we have is thawed. And so the thermistor is recording temperatures from a depth of 0 to 7 meters in this case. And every single one of those lines is a recording from that day. And so as you can imagine, near the surface where we're going to get the heat in the summer, we actually have a wider span. We're going to get really warm temperatures in the summer, warm being relative, and cold temperatures in the winter. And then as that heat or cold transcends, we've got the permafrost depth sort of moving here below. What goes through an annual freeze-thaw cycle is called an active layer thickness or active layer depth. And that's one of the ways that we can look at how permafrost changes over time. And so this is the record for the year 2000. If I leave the maximum and minimum profile from 2000 and I look at 2004, we can sort of look at how the record changes over a period of about a decade. So the first thing we can note is that we have seen a change in that active layer thickness in those 8 years, right? There is a small increase in active layer thickness. So that's telling us that now that zone between the dashed gray line and the black line has experienced thaw for what's perhaps the first time ever. So if this is happening in a landfill cover system, that's okay. But when this kind of thaw is happening in an ice-rich environment and you have ice that's now melting and becoming water, you can imagine that from a permafrost landscape or design, that could have implications. What's also really interesting, though, is just the overall temperature of permafrost. And if we look at the difference on how cold the permafrost is, we can see that there's actually quite a change over that near decade of how much warmer our permafrost is becoming. And so from a longer term and sort of the overall condition of permafrost, we could be shifting from cold permafrost to warm permafrost, which has a significant difference on how long we can expect to see permafrost here. And so one of the things a master's student, Robin Staricki, has been working on is looking at this record for the past 20 years of data or so and sort of looking at how permafrost has changed across Canada. And so she chose 5 sites, and she chose these 5 sites based on sort of the reports that were available, the materials, the type of landfill, looking at sort of the collection and the continuous data that's being collected at them. And I'm going to show you 2 plots from her work that she's recently just defended. The first is looking at what that mean annual ground temperature, so that trumpet curve I showed you, if we actually then in the middle put what the mean annual ground temperature is, we're going to get what that looks like in terms of one line. And if we plot at a depth of 3 meters, how that changes over time, what we get is a graph that looks like this. So we have temperature now on the y-axis, and we have time down here on our x-axis. Hard to perhaps see these colors. She and I have had multiple conversations about colors and graphs, but we got the blue and the red. Bar 2 and pin 1 are sort of more of our western sites. And then as we move sort of on the legend, we're moving right, we're moving east, those are eastern sites. So what we can see is, in fact, there's a little bit of mean annual ground temperature that's seen warming, but in fact, Maine, which is our furthest east site, it's actually cooling. And that's not a surprise. These are very similar records that we're seeing from the Geological Survey of Canada and some of their permafrost data that they've recently published. So this is a good news story. We are not seeing that absolute warming that's a depth of 3 meters. In terms of that active layer depth, and if that's changing by much, we can see that in fact bar 2 is seeing an increase, and it's got sort of a shorter data set. We're only plotting years that we have full data, etc. But again, in the east, we're not actually seeing a huge change in that active layer thickness. And again, that's a good sign. If we're trying to keep that active layer thickness within our cover, those are positive things. And so Robin's next question is, well, this is looking at the last 20 years, but what we're interested in is what it's going to look like into the future. And so she started looking at what will be the future permafrost temperatures marching forward. And so to do this, we've been taking projected climate scenarios and coupling that with numerical model simulations to try and actually project what some of the future permafrost temperatures will look like. So how many people feel familiar with a graph like this? Some of us? Okay. So basically what we're plotting is air temperature over time. So this is our temperature, again, is on our y-axis. We're going from 1950 all the way to 2100. So what's in gray is sort of our historical air temperatures. And then what we get is 3 lines, red, green, and blue. And basically what we're seeing are different pathways from global climate models that are saying, well, red is if we see those warming temperatures, air temperatures increasing and increasing. So we're not cutting back on emissions. And that's called RCP 8.5. And since we started doing this work about 5 years ago, they've already changed the global climate model, but I haven't had time to change the slide. So we're going to stick with our CP 8.5 for now. The green one that's kind of hidden is 4.6. So that's saying if we're sort of right now, we're starting to actually limit our emissions, we're going to do better, then we're actually going to see a plateau in those temperatures. And then blue is 2.6, which is like we're all going to now walk everywhere and no emissions and no flying, and I wouldn't be here to present, and all of those things, which are all good things, but we're already surpassing what that projection is. So for most of our work, we sort of model the red and the green line. The numerical model that we use for our research, we use TempW. And we do that because for the most part, our graduate students are going to go into consulting and into industry. And so rather than use sort of our own proprietary or our own ComSol or our own MATLAB that they're going to then shut a computer when they leave school and never touch again, we want them to get familiar with one of the industry's modeling software. So we use TempW. Now, I have to actually step back from Robin for a second because trying to actually build calibrated models started for us about 5 years ago with a PhD student, Cameron Ross. And Cam started to try and put together a calibrated numerical model. So we have ground temperatures that we can use from our sites to actually then calibrate and validate if our numerical models are working well. So he spent a lot of time thinking about material properties, right? So they're all down on this graph here. He spent a lot of time thinking about where do you start a permafrost model's temperature? And so we did everything wrong to start. He said, I'm going to project permafrost temperatures across Canada in my PhD. And he did not. But he did help us start to come back and step back and say, okay, well, what are we going to do? We have to start somewhere with permafrost temperatures. So when we model, what is sort of a good best practice for that? And so he spent time thinking about the initialization of thermal models in cold and warm permafrost. And I won't say anything more about that. So I apologize if you love modeling. We can talk about it during questions. The next thing we realized we were doing wrong was how deep our models needed to be. And so he spent another year of his PhD thinking about the depth of his numerical model and what the geothermal heat flux, which is the heat that's coming from the center of the earth, what that value should be, where it should go on our model. So is my model 10 meters, 50, 100 meters, 1,000 meters, and does it change? And in fact, we found out some interesting things in that, yes, it does change, and it's important that we actually consider it. But what's really important is actually considering how deep our models are. So as a graduate student, you're like, the shallow models run faster. So I'm going to do a shallow model. And we started doing a shallow model. And then it got deeper and deeper. And eventually he was doing 1,000-meter models. He didn't stay at 1,000 meters, but we realized it's really important. And why is it important? Is because we're not just talking about the top 10 meters of permafrost. So the New York Times ran a really interesting storyboard in 2017 talking about permafrost in Alaska. And it says Alaska's permafrost shown here in 2010 is no longer permanent, it's starting to thaw. By 2050, much of this frozen ground, a storehouse of ancient carbon, could be gone. And this is what may be lost. This is a significant land area to be lost from a permafrost perspective when you think about the infrastructure that is in this space, the pipelines, the designs, everything that's in there. If they say that the permafrost is going to be lost, that has huge implications. But during Cam's modeling process through COVID, what he realized was that he too could lose all permafrost by using a 10-meter model. And so here we are starting at the year 2000, which is the trumpet curve that's got the yellow stick on it. And if we apply the warming air temperatures of 2.6 or 8.5 at a model that's only 10 meters, we are basically on our 0-degree line, right? We've saying that we've lost permafrost. And so he said, yep, I can do what the New York Times model did. I can lose our permafrost in lots of areas. But if my model to 25 meters, I start to see that there is still some permafrost there. And by going down to 1,000 meters, we realize how much permafrost is still in our ground that was not getting captured properly by a shallow model. And so we realized that, in fact, the model that they were using was no deeper than 10 meters. And in fact, when we went in and dug into the actual work that they did, it was the Landsat model, and they were at that time only doing to a depth of 10 meters. And so it's a really interesting sort of full circle for us to be able to say, we understand what's happening, we can see what's been published, and we understand how deep our models need to be. Now, nobody wants to do 1,000-meter models, so he figured out how to actually change your geothermal heat flux over time, and you can actually do shallower models. But again, I don't want to go into the weeds of numerical models because I already see some glazed faces, which that's fair and fine. So the type of research I like to do is really an applied-based research, is to take some of the lessons and actually apply it to cases and to applications that are going to occur in the field. And so the first application that we used with our numerical modeling was, as you can imagine, a cover system. And so we're going to look at a waste cover system at one of these. We're actually two of these dew line sites. But I'm not going to tell you which ones because D&T has asked us not to talk about which specific landfills are doing well and which covers might need to be thought about sooner than later. So here's a thermal analysis of a waste cover. And basically we have just a generic sort of schematic of what one of those waste covers looks like. So we have cover material for some of these landfills. The material is basically the material that was there on site, and we have the waste below it. And the idea with one of these designs is to keep that active layer within the cover so that the waste is staying frozen year round, and any active layer thickness, any active layer that's changing, any thaw is happening within the cover. Now that is not the only way these are designed. There's other ways, but that's sort of, for the framework of tonight, what we're going to talk about. With the thermistor cables that are recording the temperatures, this is the profile of the active layer thickness that we get in 2003 up till 2023. And so what we can see is that the active layer is within the cover. These are performing well. So then Rob and Stricky took this future climate modeling and then applied it and said, okay, so how are these going to look in sort of 75 years under different warming scenarios? And so at projected site A, this is what the cover performance looks like under an RCP 4.5. So by the year 2075, we're still mostly within the cover. And we can see that maybe by about 2075 for RCP 8.5, near the surface, we're going to actually have near the top of the cover, maybe a little bit of additional thaw that's happening and getting into their waste, but for the most part, it's still within the cover system. Whereas for projected site B, we sort of have a very similar start right now. It's performing well, but even under RCP 4.5, by the year 2100, we're active layers now going well within that waste. And for RCP 8.5, we basically end up with a thermokarst that's developing, and we're basically now going to have material that's not freezing back in the winter anymore at all. This isn't necessarily a bad news story. This is actually a good news story, because what this is showing us is that there's some landfills and cover systems that are doing really well, and the intervention and adaptation that might need to be done is quite limited right now. But what we can do is we can provide the information back to D&D And they are now going to be able to start to go target the areas where the landfills are going to need intervention sooner than later. So that's what we love to do, is we like to sort of talk about our research and then bringing it back and hopefully helping and support, in this case, a design that exists and see what we can do moving forward. Okay, the second application is thinking about foundations. So I'm jumping now to the ITH, the Inuvik-Tuktoyaktuk Highway, which is in the Northwest Territories, to a place called Gunny Creek. You might not think it, but you've seen it before. So in 2011, this is what Gunny Creek looked like. All right. And so the ITH is now an all-season road. It's open year-round, but prior to that, it was a winter road. The route wasn't exactly the same, but at Gunny Creek, which is really close to Tuk, this was where that winter road went. So that's why this culvert existed on the ITH before the all-season road was there. When they actually started to think about not replacing this for the third time, they actually changed the design entirely. And this is what Gunny Creek now looks like. So they've removed the culvert and they've replaced it with a concrete buried arch and thermosiphons. So the concrete buried arch is built on adfreeze piles. Some are 15 meters, some are 18 meters. This is sort of a picture that was happened during construction, and that was in the winter of 2021. And so despite the fact that we had grad students already and planning, sort of leaning into this winter, that they were going to install instrumentation, they were going to actually strain gauge the piles, they didn't, because it was COVID, we weren't allowed to travel. So they were doing numerical models in their basement. But we have these pictures, so now I can talk about the construction, even though I wasn't able to be there in person. 20 piles per side, and voila, you have Gunny Creek. And so we have had the opportunity to go since. But one of the things we started to do was look at the thermosiphons. And it was COVID, material was hard to move, it was hard to get to, and it was within a 5-day window that they were going to be on the go, no-go for installing the thermosiphons here. And so if we take a look at a cross-section of Gunny Creek and do a bit of a schematic, this is a schematic we can have. So we can see the thermosiphons, we've got a slope of material, sort of these 2-meter wide concrete arches, and we've got black lines and blue lines. The black lines are those adfreeze piles, and the blue lines are the thermal probes, so the probes that are coming down from the thermosiphons. Thermosiphons, Jim, how does a thermosiphon work? And what does a thermosiphon do? Yeah, I mean, yes.
Carbon dioxide goes down to the ground, and the ground is cold to -5, and the carbon dioxide is always cold down here for to evaporate. And during the evaporation process, it draws to the ground. As a vapor, it rises to the top, which is called the radiator, and in the radiator, it encounters air temperature that's -20. So the vapor says, oh, that's really cold. I'm going to condense, convert into a liquid, expels the heat. The liquid drops back down to the bottom of the radiator, which is called the evaporator. And it says, oh, it's -5. It's warm down here, relatively warm. I'm going to evaporate, draw more heat. And it cycles throughout the winter. In the springtime, when the air temperature is 5, the vapor goes to the top into the radiator. And it says, oh, it's warm up here. I'm going to sit up here as a vapor for the summer. The thermosiphons are passive, non-operating for the summertime. Then in October or so, when the air temperature gets cold, the whole cycle starts again. And they work continuously without electricity or power for years and years and years. For example, there's the TAPS, the Trans-Alaska Oil Pipeline, has 36,000 of these along its length. Some of them that were installed in 1977 and are still working.
I mean, thank you. That's what I mean. I'm going to get the experts to talk about this, right? And so one of the things that our graduate student Belosa did was she said, well, what happens if these thermosiphons are there compared to what happens when the thermosiphons aren't there. And so she spent time doing some numerical modeling of that. So what I'm going to show you first is the temperatures that she built in her numerical model for January 1st, 2024. And so the first, we're going to look at when there's no probe. So there's no thermosiphon, right? So we're not cooling the ground along that probe. I mean, it's 2024, it's January, things are cold. We've got really cold temperatures near the surface. It is a bit warmer as we're going down this profile, but we still have cold permafrost. With the thermosiphon, we can see how much colder those ground temperatures are, right? So exactly the system that Jim was talking about, we're cooling the ground. And from an adfreeze pile perspective, right, where our adfreeze pile is really that strength is because we have frozen ground holding on to our pile. We want that ground to stay as frozen as possible. She then applied those warming air temperatures to the top of her model. And in January 1st, 2100, if there's no probe, what we can see is that along that sort of, there's a, well, I'm not going to do that, right? Along here, where this is sort of interacting with that pile, we see warm temperatures, right? We're not really even seeing much permafrost now anymore at all. But with the thermosiphon, even though we have warming temperatures and air temperatures at the surface, we can still see that green line. So we still have temperatures that are looking at about -3 around that pile. And that's a really good news story. Because the rule of thumb that we use, that sort of Ed Hove, I would say, is the guy that talks to us most about this rule of thumb, is that at a depth of 10 meters for these adfreeze piles, providing the temperature is -1 or colder, then we should still have that adfreeze bond strength. Once those temperatures get more than -1, warmer than -1, that's when we're going to start to lose that strength. And it would be like pushing a popsicle stick into warm clay versus a popsicle stick into really hard ice cream. Bad analogy, but hopefully you can kind of visualize the difference I'm talking about there. So what we do is we were looking at what does, at a depth of 10 meters, what do the temperatures look like for those two scenarios? So the green line being with no thermal probe, thermosiphon, and the blue with a thermal probe. So what we can see is the difference is actually quite substantial. Had those 5 days come and gone and the thermosiphons hadn't been installed, based on the current conditions of the permafrost at this region, and with no thermosiphon actually trying to cool the ground, we would have reached that -1 in like 15 years. So not necessarily the best return on investment for it's replacing that culvert. However, the thermosiphons are there, and the design is sort of indicating that they should still be at a temperature that is going to have that adfreeze bond strength up until 2080. So that's fantastic. Even though we weren't there, we were still able to send up our monitoring instrumentation, and they actually were able to install thermistor cables into the ground. And so we're also currently monitoring this. And if we plot the measured temperatures at that depth of 10 meters, what we have from 2022 and 2024 is a really good sign that we still have very cold temperatures. We're plotting along with a thermal probe. This also means that we're collecting data that's going to allow us to improve our numerical model and sort of keep monitoring it and moving forward. And then what we did this past sort of 2 months ago is we actually went up and we took a whole bunch of our sort of numerical modeling students who had been thinking about numerical models but hadn't actually been to site. We went up and looked at Gunny Creek, downloaded the data. So some of them are processing that now to add on. So what's going to be our 2025 data set. But also we were able to take some really neat thermal images that do show these thermosiphons are working, right? So they're red, well, yellow, I guess, which are showing that they're much warmer than the air temperature around them. Now, -40, it's hard to get colder than the air temperature that day. But that's a really neat sign to sort of look and say that the thermosiphons are indeed working. Okay, the third application would be to talk about some snow and embankments, because one of the largest influences on our ground temperatures are the snow, right? So snow acts as this beautiful, warm, insulative blanket, and how we use it and what we think about it in terms of our thermal modeling and in terms of what we do for design is important. And we're working with the NTGS and Alice Wilson on the influence of compacting snow and how that can actually change the ground temperatures. And so we're looking at moving that forward, but in light of time, I don't want to spend much time talking about snow compaction. But I will say that Robin spent all this time thinking about the temperatures of permafrost across Canada, and she spent time modeling those. And I'm not going to sort of show that work today, but I am going to give a little plug to Robin, because what she realized is that snow was both the bane of her existence doing numerical modeling, and that the projections that Environment Canada, of climate change of Canada, are giving are so varied and so wide ranging that what you pick has a huge influence on the thermal temperatures that you're receiving out of your numerical model. And so if you're going to be at Geo Manitoba, she's going to be giving her talk on that in her paper. And so I encourage you to go and attend and listen. So like any good research, questions lead to more questions and more fun. And so from sort of the applied thermal modeling and some of the applications we were doing, we started to think about some of those pieces in more detail. And so add freeze piles and sort of how they work. And again, Jim is talking lots about this, but one of the questions they have is if it's, once you're reaching -1, what's going to happen? And so we're doing work at Hans Creek, which is a bridge along the ITH. So the Tuktoyaktuk is up where Gunny Creek is, and Hans Creek is actually reporting temperatures at their bridge piers that are at -1 and warmer. And so this summer, we're actually going to install one thermosiphon to actually monitor the influence of one thermosiphon and how that might actually change with the creek flow and the water, and start to investigate that. And my colleague, Greg Seaman, does a lot of work with geotechnical centrifuge, which is basically like taking a small physical model and spinning it, replicating that on a much larger scale. And so he's looking at add freeze pile strengths using centrifuge, which is really cool, and has found some interesting results from that as well. Sort of branching off of our cover systems and our work with D&D, the question they've asked us is, well, what's going to happen if we have some of this waste that becomes unfrozen? And they're thinking about it in terms of what's going to happen for even just a fuel cache, right? We have oil drums that are left in the military, in the CAF, and sort of on Eureka, what they've left. What is going to happen if they're actually having these contamination and migration into the soil in our systems? And so working with a colleague at Queen's, Kevin Mumford, he has a really interesting light transmission technique where you have a thin soil sample and you shine a really bright light behind it. You can actually quantify the degree of saturation of your sample. And so he does this thinking about gas hydrates and everything. And I said, well, let's actually freeze it. So we took it, we threw it in a freezer. And then we had a student, Major Alex Lefebvre, who then spent time looking at how does LNAPL migrate in frozen and unfrozen systems. And so what I'm showing there is a result of him spilling some LNAPL into a frozen sand pack that is saturated at the bottom, right? That's that bright light that's coming through, and it's unsaturated at the top, which is that darker color. But probably the most interesting thing that we found was this halo band that was occurring on the outskirts of LNAPL, right? So the LNAPL is coming in and it's pushing out the unfrozen water in our permafrost system. And so this is giving us a first chance at actually looking at the unfrozen water in permafrost, which has a really cool side when you're thinking about water and hydrology in these cool systems. And then the final one sort of that spawned from here is looking at those large scale landforms, those retrogressive thaw slumps, and how do we understand the mechanisms that's triggering them? And these are large processes, and there's a lot of work that's being done right now on actually quantifying and mapping where these are occurring. But with our engineer hat on, we want to say, yeah, but why? Why do some of these self-stabilize, and why do some of these continue to retrogress? And so what we're doing, again, is using that geotechnical centrifuge to try to simplify for sure, but replicate some of these processes in the lab. So here's a picture that was taken by Robin when she was out in the field. And you can see one of her colleagues, just to put it in scale, is up here, right? So that tiny little orange dot's a person. So just to give you a scale of how large these systems are. And then Greg and I have a PhD student, Ozin, who's then taking a simplified version of this and putting it into the centrifuge. So she's taking a frozen block. Let's see if this plays. So frozen block of clay. she puts it in the geotechnical centrifuge, and it's thawing. And so you're going to see the deformation as this thaw happens. There's a little bit of thaw consolidation. There's some cracking at the surface, and then we get a sharp failure that happens. And so she gets some events that are toppling, where we're actually getting that toppling effect happening. She gets some that are sort of more of a slumping failure. And then she gets some that don't fail at all. And so she's investigating what are some of the triggering mechanisms that change these different modes of failure, right? What takes it from a shearing or a slumping failure into no failure at all. So that's really exciting stuff that we're doing right now with AUSM. Okay, and then I'm going to shift. Does everyone have about 10 more minutes in them? Yeah? Okay, I'm going to shift to a topic which I think you've had a chance to hear about already this year, and it's looking at a very unique railroad in Canada. Did you talk about the rail? Oh, you didn't. Okay. Pardon? Not here. Okay. So I'm going to talk about a railroad that I have a wonderful opportunity to work with Dr. Jocelyn Haley on as part of a Permarail project. And so this is looking at the Hudson Bay Railroad. So this is a map that shows the network of rail across Canada, and the Hudson's Bay that we're going to talk about goes from the Paw all the way up to Churchill. It's about 820 kilometers. There's more that's the extra arm, but I'm not going to spend time focusing necessarily on that. So this is the Hudson's Bay Railway, and it travels over very unstable substrate, right? You've got peat, muskeg, and permafrost. So this is work that's being done by some of our graduate students, and this is Captain Ji Woo has said, I don't like your crayon sketch that you keep showing. I'm going to improve that. And so this is her permafrost map that's sort of based on the ice map that Brendan O'Neill did. And what we can see is that the Hudson's Bay Railway goes from the Paw, which is down here, in sort of this isolated permafrost, no permafrost, through discontinuous and all the way into continuous permafrost. And so you can imagine some of those things that we've seen and looked at about permafrost, how that's going to go for a rail. And so the area that both Natalie Arpin and Ji Woo's work that I'm going to show, we sort of focus on this area up here in the discontinuous permafrost in the Herkimer subdivision. So this is a picture of what that rail looks like and sort of the landscape that it's in. And so it certainly dramatically changes as you go, but we've got thermokarst lakes, fens, peat plateaus, and a group of students have gone, and so this is where Constantine is, the winner. He's on the Hudson's Bay Railway right now doing research for Jocelyn and the work that they're doing. And then there's another faculty member, Pascal Roy-Levier, and so she's at Laval, and she looks at it from a geomorphological point of view. So she's looking at what is happening in terms of the permafrost landscape, what's happening with these thermokarsts and the lakes, and how do those interact. And so her PhD student, Tabitha, has done some really interesting look at ice wedges that develop in some of these areas in these polygonal terrain. And this is one of the cores that Tabitha is showing. So what can we all see in Tabitha's core? I hear it here. We got a lot of ice. Yeah, a whole bunch of ice. And so today I'm going to talk about two cases that we're looking at in terms of the work that this group is doing along the Hudson's Bay Railway. And it has to do when ice is forming, and it has to do when ice is melting. And so the first one is actually when ice is forming. This is a Horn Creek crossing located at mile 419 of the Hudson's Bay. It's in the discontinuous permafrost zone. It's a four-bend steel, I have to read this, four-bend steel bridge constructed on H piles. And you can probably see from this picture that it's not quite level. Perhaps even more in this image, we can see that it's really not level at all. So it's undergoing significant frost jacking. And in fact, it had reached up to a half a meter of frost jacking. So Andy Take, who's another researcher on this Permarail project, he and I are co-supervising a PhD student, Natalie Arpin. And she came on and saw this and said, yes, I would like to study this bridge and study this frost jacking and try and understand what's happening. So she's been to the field a number of times. She's installed instrumentation, shape arrays, tilt meters, thermistors. She's done LiDAR. She's really trying to understand how this frost jacking is happening, why it's happening at one pier, not others. And it's a really interesting case study. You can see, though, that this isn't the first bridge that has been at this crossing. And recently, the owners of the rail said, this bridge is also not going to stay like this. And so what happened after 2 years of Natalie's PhD is that they fixed the bridge. So they fixed the bridge, but they did not fix the problem. Their job was to keep the rail operational. Our job is to try and understand why we're getting this frost jacking. So what they did was they jacked up the bridge, they cut the piers, they lowered the bridge, and they got this. So for any of you who have done grad school or helped supervise or had a student working on a project, when you have somebody cut down your research project, that can be a bit disheartening, but you flip it and say, not many people get to zero their data during their PhD. This is exciting. And so Natalie has continued to monitor this bridge. And because they fixed the bridge, but not the problem, what we see is that we are still experiencing extensive frost jacking and subsidence that happens over the course of a year. So in the top, we have the tilt meters that are installed on each beam. And then we have sort of the elevation over time for that one pier. So Natalie is still able to continue to monitor a pier that is frost jacking, and she's trying to understand a little bit more about why that's going on. The final thing I'm going to talk about is sort of the inverse, is when you have that ice in that core and it melts and it goes away, and you have what you can imagine is significant thaw subsidence. And the HBR, the Hudson's Bay Railway, they call these sinkholes. So this is at a location that was once called John Sinkhole and then became Jiwoo Sinkhole. And you can sort of see there's an instrumentation block over on the side, and there's a shapery that's monitoring, and there's a weather station sort of further behind. And John was a master's student that started and picked this site as an interesting location to monitor a sinkhole over time. But it's hard to maybe say, like, why? What's going on at this site? What makes it special? So if we change our viewing angle, this is the same spot. We still got the shape array. We've got our instrumentation box, but this is what the rail looks like, which is probably not what the rail looks like in town here in Calgary. This is regulated by Transport Canada, right? They have to follow all of the same regulations. So what this means is when you have rail that looks like this is you just have more slow orders, and you have to go slower across it. But sometimes when there's a certain threshold that's met or exceeded for this track geometry, then you actually have to intervene and do maintenance. A lot of these sinkholes happen at these transition zones where we're going from a peat plateau to a low-lying fen. So the peat is staying frozen, and that low-lying fen is experiencing thaw. And so that's when we're going to get a sinkhole that's happening, is between those transitions. And again, here's just another figure from Jiwoo's thesis, where she's sort of just showing the size and scale of these sinkholes. And so Transport Canada regulates that HBR takes track geometry, which is collecting a whole bunch of information about the rail itself, and they have to do that every month. And Jiwoo and John have spent time looking at one of the parameters they collect, which is called surface 62. And so this one very clearly indicating this is being stretched. This is not what the sinkhole looks like, but to try and actually figure and show what surface 62 is, we've stretched the figure a little bit to amplify that sinkhole. But surface 62 is a 62-foot core. And what you're doing is you're measuring the vertical surface deformation in the middle of that chord. And so John Gallagher, he spent time doing a workflow that would take this surface 62 data and start to process it across the rail. And so basically this is his workflow. If you're really into rail, I'll happily walk through this and how it's all going. But ultimately what we get at a sinkhole is can you guys see that? I can't lift it up because it won't change. But it's this sort of curve. And what you're getting is perhaps a peak in your data. So you're getting a peak in the surface 62 data. And that's what Transport Canada says and uses from a regulation point of view. And so if you've reached and exceeded different classes, that's when you have to actually slow the train down. So this is an example of 1 mile data for surface 62. So this is mile 424. So this captures that John and Jiwoo sinkhole, which is highlighted there and has the X. And this is what the data looks like. And so on this month, you can see that they actually exceeded class 2 threshold twice. So both of those sinkholes, as the track geometry truck goes by, they get out, they mark it, and then the maintenance crew comes in behind, they lift the rail, they reballast, they tamp it, put it back, and now they can continue and they can have the trains roll at a faster speed. So looking at surface 62 and these sinkholes is not anything new. Back in 1987, when EBA was doing some work and doing a lot of understanding of what was happening with these sinkholes, I see Sam sort of, maybe, yeah. Yep. They actually, and we're going to talk about the thermosiphons that got installed, they looked at where these sinkholes were happening. And so what John did was he said, well, how has that distribution changed over time? So in 1987, you can sort of see where the majority of those sinkholes were and sort of how many they were in numbers. And in 2022, we can see that there's a significant increase in the number of sinkholes that were occurring, and we can see that it's shifted further north, right? This is not shocking. We can imagine as we're getting warming climate from 1987 to 2022, we're going to see sinkholes start to happen further and further north. But what Jiwoo was interested in doing was actually trying to look at the rate of these sinkholes. Because from a maintenance point of view, what HBR would like to know is, well, which sinkhole am I going to have to deal with next? And can I actually be a little proactive? And if I know what the rate of these sinkholes are, can I actually get ahead of it and start fixing it as my maintenance crew goes by and improve our maintenance practices? And so she started to monitor this sinkhole over time. And as she built the data sets, you can see that we have it rising. This is 45 data sets. And when it drops, that's when they've done some maintenance. And so if we took the peaks from that one sinkhole that's highlighted in gray over all of those 48 data sets and plotted them, we would get a graph that looks like this. So that's that max peak at John and Jiwoo sinkhole over time. And we can see how that changes. Now what we've done is we've highlighted all of the times where our sinkhole actually decreases, right? Our surface 62 decreases, which means they've gone in and done maintenance. And so if we erase all of our maintenance, which is going to have an influence on the rates, and then string this together, what we can start to do is look at the rates of our deformation during seasons where we're not doing maintenance, right? So in the summer, when they're doing a significant amount of maintenance, we're not yet able to quantify what the rate of change is. But if we take a look at what's actually happening, we see that there's a lot of change that happens in the winter, even when we expect things to be frozen. But in this case, we actually also see that the rate is decreasing. And at a rate of 1.88 inches per year, that means that that sinkhole would no longer be crossing our class 2 threshold and would no longer be an issue for them. So that's a good news story. And then as you do is you start to think, well, that's one sinkhole. How do the other sinkholes in that mile look? And so Jiwoo said, let's start to look at how other sinkholes within a very similar environment, very similar air temperatures, climate, etc., how do they perform? And so looking at 3 sinkholes, we can see that they're actually performing quite differently. And so that really helps us to understand that it's going to be largely influenced by the ground and the permafrost below. The maintenance hasn't changed at those 3 sinkholes over that period of time. They're in the same mile, they're happening on the same day, it's going to be the same crew. And so we can start to understand whether or not it's going to be maintenance practices or whether or not it's going to be permafrost degradation. And then what we can do is we can start to help them understand which sinkholes are going to have challenges and when. And the last thing I'll sort of address is looking at some of the work that's being done in the HBR to try and mitigate these sinkholes. And so Jiwoo looked at 3 different things: thermosiphons, geocells, and routine maintenance. Now, full disclosure, the geocells that were installed were not installed to try and limit sinkholes. They were installed because in 2017, 2018, there was washouts, huge flooding and washouts of the rail, and it wasn't operational. And so in order to get it operational, they used geocells as ballast, support, in order to actually quickly get the rail back open, and they did that in like 60 days. So thermosiphons. So these are thermosiphons that were installed back in the 1980s, early 1990s, and they were put at the locations where at the time they were having all those sinkholes. So these are now much further south. These thermosiphons have not been maintained. They have not had additional CO2 or gases added. But as Jim said, these can work for a long period of time without that maintenance. And in fact, they were there, Justin Panakwa, I did not pronounce that right, with Arctic Foundations. He was up there with HBR and looking at the performance of these thermosiphons, taking thermal images and saying, yep, there's some that are still working. Some are broken, some aren't, but that's a really good news story in terms of the thermosiphons, longevity, and the fact that they're still keeping the ground cold. But what's interesting is that they're still keeping the areas that they're touching cold, but the area where they're not, these sinkholes are now happening and sort of developing in between all those thermosiphons. But that is a challenge for the next master student and not Jiwoo. She also looked at geocells, and we've also looked at geocells in terms of coupling it with thermal temperatures and what the thermosiphons, what the geocells will do over time. And then she was comparing that to sort of routine maintenance that happens on the rail where they're going to reballast. But I'm at slide 131. And so we're not going to talk about what Jiwoo found between the thermosiphons and geocells and routine maintenance. I'm happy to show you afterwards, but if you're, I'm sure I'm tired, so you guys all must be exhausted. Okay, so the final quick thing is just thinking about sort of built to last. And I added the question, it wasn't part of my talk when I did this back in Montreal, but I think it's a really important one to ask is we have infrastructure that's being built, and some of it's performing really well in permafrost regions, and some of it is now going to start to see some challenges as we get these warming temperatures. And so we looked at a whole bunch of different things that are happening. And my hope is that sort of today I've walked you through how some of us are using numerical modeling, field work, and lab studies and physical models to try and better understand how infrastructure that has been built is going to perform, what kind of mitigation and adaptation techniques can be used marching forward. And because I promised my kids they'd be in it, when you put pen to paper and think really, really hard, the hope is that as we improve what has been built, is that across Canada and across permafrost, even though we might see warming temperatures, that we will continue to improve and understand this knowledge, and that everything that we build from here on in will be built to last. So with that, I can't finish without thanking all of the different groups, people, and certainly all of the funding that has gone into this work. I'm not going to go through everyone here, but it's certainly, I've been very, very lucky with the support for my students and this research that we've been done. I also have to take a second to thank my colleagues, because without them, this wouldn't be possible. And so colleagues, you're sort of here all with your colleagues. These are my colleagues, some are in this room. But I have to thank them because they're an inspiration and have taught me and have been my mentors. But really, everything you've seen tonight is due to the hard work, tenacity, and sort of the brains of my graduate students. And without them, this work wouldn't have been possible. And so I would really like to acknowledge the fact that what you've seen tonight, all of the good research and the amazing things they're doing is thanks to them. Anything you have questions about or things that I've done wrong is thanks to me, and so we can have those questions after. But yeah, so a huge kudos to my graduate students and the work that they've done. So with that, I would just like to say thanks so much